Hello physics students. The topic of today's video is the electric field. Now a couple videos ago I told you that if you had two charges, they created a force on each other. If they were like charges, like a positive and a positive, they repelled each other. Same as if you had a negative and a negative, they also repelled each other. But opposites, like a positive and a negative, attract each other. And we learned an equation, Fe equals K Q1 Q2 divided by r squared for the magnitude of that interaction. But it turns out that that view of how these charges interact is much too simple, much too crude. In other words, it's inaccurate. Let me give you one situation. Suppose I have two electrons here, minus minus. We said they repel each other. But it's possible to move one of the electrons away extremely rapidly. And what you would find in such a situation is that this electron would still feel a force away from this point over here, even though there's no charge over here. So that must mean that something else during that time is creating the force. That something else is the electric field. So what is an electric field? It's essentially a disturbance in space. The charge somehow changes space. If you have a positive, then all around it, it creates this electric field. And it's thought of as a vector, an arrow that points away from positives and towards negatives. And there's a pattern to this electric field. Notice that at this distance, right near the charge, all the arrows point away, but they're the same exact length. If you step further away, all these arrows are also the same length, but shorter than the original ones. Go even further, even shorter arrows. So it gets weaker the further you get from the charge. And the same pattern holds for the negative charge. So what I want you to do, I'm going to create a pause. Go ahead and copy these diagrams as accurately as you can into your notes. Okay, so let's now look at how the interaction really happens. Again, we used to say, if I had a positive over here and a negative, opposites attract. So this negative is going to accelerate toward this positive. Now let's look at it within that same interaction from the perspective of electric field. What really happens is this positive, as we saw over here, creates an electric field pointed away. So charge 1 creates electric field from charge 1 pointing away from it. Charge 1 creates E pointing away from itself because it's positive. The magnitude of that electric field is KQ over R squared. I put the 1 here, but typically they don't have it in most books, but I'm just put it there for clarity that electric field came from charge 1. Next, this charge doesn't respond to this charge directly, it responds to its electric field. So charge 2 experiences a force. And which way is the force? Well, because it's an electron, it goes opposite of the electric field. So it feels a force, as we could see here. The magnitude of that force is given by Q of charge 2 times the electric field caused by charge 1. So that's really how the interaction occurs. Let me create a pause to allow you to copy this down. I want to emphasize again, we got the same answer as before. We would say this minus moved to the left because it was attracted. Now we add another step to the thinking to be more accurate to how the universe works. We say, no, okay, charge 1 doesn't pull it directly. Charge 1 creates an electric field, and that creates the force, same as opposites attract. Furthermore, if you plug this whole formula in right here, you see you get the original KQ1 Q2 over R squared. So why do we do this if we get the same answer? Well, we get the same answer in this case. But in a lot of examples in physics, you get different answers by calculating this electric field that are correct, and the other way is not correct. So where is this on the reference table? Is it on the reference table? So sort of, okay? So here we are in the electricity section. And let me give a moment for the focus. And you see the second formula down is electric field is F over Q. That's basically the formula. I had F equals QE. It's the same formula, okay? But they don't have KQ over R squared, but they have this formula. If you put these two together, you get KQ over R squared. In other words, take this formula, divide out one of the charges, and, well, let me go over here. And when one of the charges is divided away, you get KQ over R squared for the electric field. So it's sort of there. You have to put the pieces together to get that formula if you need it, okay? All right, now let's do one example. So example 1, determine the electric field 3 meters from a -4 microcoulomb charge. Then we're going to determine the force on an electron at that point, and then we're going to determine the acceleration. So before, in the previous video, we would have done, for force, we would have just did KQQ over R squared. We would have gotten this force directly. But first, today, we're doing the electric field. But before I jump into the details, again, this negative creates an electric field towards it because it's a minus sign, like here. And then this negative experiences a force in the opposite direction of the electric field, which is how like charges repel. If this were a proton, it would feel a force with the electric field this way. In other words, it would attract to the minus. Opposites attract, like the way we said before. So we get same answers. But let's now calculate the electric field. KQ over R squared. We take Coulomb constant K, 9 times 10 to the 9th. Front cover of the reference table, right where my index finger is right here. This 4 microcoulombs, I mentioned this already earlier in another video. If you don't know what a micro is, front cover on the bottom left, you could look up micro, and it's right here, 10 to the minus 6. So that's why the 10 to the minus 6 here, because of that symbol. And then the 3 meters. And we now punch that in a calculator. Oh, I need to create a pause to allow you to copy that down. All right, so we get as an answer, E equals 4,000. It's not uncommon for electric fields to get into the millions in examples. So we'll see that later with other examples. B, determine the force on the electron at that point, on a electron. So the force caused by an electric field, and I'll put a subscript E, which is what's on the reference table for the electrostatic force, and I'll drop the number subscripts, but basically it's QE. Now, the Q on an electron. I mentioned this in the charging video. You will not find it on the reference table, but what you will find is right here, 1 elementary charge. Okay, where am I? One elementary charge right where my finger is, and then on this side you can see the 1.6 times 10 to the minus 19th. That's the 1 elementary charge. So that's the charge on an electron and a proton, symbol lowercase e. But it's an electron, so 1.6 times 10 to the minus 19th coulombs, and the electric field is 4,000. I forgot to mention, I did not plug in the minus here, same like when we were doing Coulomb's law. You don't plug in the minus because the minus is just used to tell you whether the electric field points left or right, towards or away from the minus. In these formula calculations, just calculate the magnitude. Well, if you punch this on a calculator, you get Fe equals 6.4 times 10 to the minus 16th newtons. All right, there's the force on that electron right here at this point, opposite of the electric field. The last part, determine the acceleration. Well, the formula is in the reference table, but I'm not going to rush over to the camera for this because there's something else I want to get close for. F net over m, Newton's second law. Hopefully you remember that in the top of your head, but it's okay if you don't, because again, you always have your reference table for test and Regents. So this force is like any other. It creates acceleration. So I can just plug it right into Newton's second law. But the mass on an electron, I think I mentioned this much earlier in the year. Reference table, front cover. So right here, where my index finger is, let's give a moment for the focus. You see the rest mass of an electron, and then you go over here and you see the 9.11 times 10 to the minus 31, right? Rest mass of an electron, 9.11 times 10 to the minus 31 kilogram. You can see here also the proton and neutron mass are also on the reference table here. So I get the mass of the electron, 9.11, 10 to the minus 31 kilograms. I punch that on my calculator. And I get, what was it, 7.03, I believe, times 10 to the 14th meters per second squared. Oops. Let's fix that up a little bit. All right, so let me create a pause to allow you to copy that down. All right, couple other things. So that was one example. I'm not going to do another example, but I just want to point out that it's very common when you're getting into these later topics in the year for the Regents to mix in the old information, like you see Newton's laws. Here it comes up months later in this problem. That can happen. Another thing that can happen, especially on the homework for tonight, is there's a lot of kinematics mixed in. So don't forget D equals 1/2, oh no. D equals VIT plus 1/2 AT squared. That's on the back of the reference table that we were using for the first half of the year. Remember that when something begins from rest, this term you could cross out. Also remember V final equals V initial plus AT. And the VF squared formula. Any of these can pop up on the homework for tonight. You might want to jot them down. Maybe I'll create another pause. But of course, you don't have to. They're on the reference table. Okay, so that's the electric field. You don't say, well, you could if you want to be, just quick about it. But if you want to be strictly accurate, you don't say opposites attract and likes repel. You say a positive creates an electric field away from it. A positive feels a force with that electric field. That's why it repels. Or positive creates an electric field away. A negative feels the force opposite way. Opposites attract. So it's another step in the thinking. You do an extra calculation. E equals KQ, not both of them, KQ over R squared. That's the electric field caused by charge 1. And then the force caused by charge 2 is F equals QE. You put it together and you get a more accurate, more complete picture. Now what I want to do is, that's just all you need for the homework. But there are some demonstrations that I would have shown you if I was in class. So I did them with another class. So I'm going to use the time machine again. Hopefully not getting sick of the time machine. But I'm going to send you back to see the action of a Van de Graaff generator. The first about 9 minutes or 10 minutes will be me showing you the Van de Graaff generator working and then explaining why it builds up charge, how it does, and then how it makes bolts of lightning. And when there are notes there on the board, I want you to copy them in your notebook because that's part of our curriculum too, the Van de Graaff generator. So those 2 boards, you're going to add to these notes. So, brace yourself. Here we go. What I'm going to do now is use these 2 metal spheres. This is called a Van de Graaff generator, to demonstrate those principles in action in pretty dramatic form. So you've probably seen this already, but it's fun watching it again. So here we go, I'll turn this on, and there's a rubber belt that's going up into this outer metal, and you may not be able to see that, and then what happens is it's charging this conductor on the outside, and then it's creating little lightning bolts. The lightning bolts are going into this conductor over here, and you can't see it because it's off the camera view. There's a wire that runs to a sink here. When I zoom out later, you'll see the wire connected to the sink. The reason why is the wire connected to the sink is what we call a ground. The metal pipes literally run into the ground, into earth, so that the excess charge of this Van de Graaff can go into here and then go into the earth and neutralize. So let's watch these little lightning bolts in action, and to increase the dramatic effect, what I'm going to do is turn out the lights, and hopefully we see a nice little display. I'll let it run for a while. Nice to watch. Nice one. Some of the sparks are really beautiful. Turn on the light again. Shut off the Van de Graaff. While this is a fun little toy that we could play with and generate sparks and do all kinds of fun stuff with, we do use it in this class to study our physics and understand more about conductors in static equilibrium. So what we're going to do is I'm going to describe and explain how this even works in the first place. Because the sparks were jumping electricity, electrons between these metals through air in between. And normally air does not conduct. Okay? So we're going to answer the question, why does the air suddenly conduct electricity? Like, for example, if I put my finger next to an outlet, I don't get electrocuted unless I stick a conductor like a paper clip into the outlet. Then I get electrocuted. Air, I could put my hand in, electricity doesn't jump through the air. Why does it jump through the air here? And going back a step before that spark even occurs, how does this even work? How does it generate enough electricity to shoot little miniature lightning bolts? So, that's what we're going to learn next. Let me just get these out of the way. Don't worry, they'll come back. Charging a Van de Graaff generator. This is going to explain how it happens. So before I explain and go into the explanation, I want to first point out something, that this sphere is hollow and comes apart. The inside's very interesting. You could see the rubber belt in here coming up through the plastic here into the conductor, and then there's a pulley up here, but also a metal screen right here, like the kind of screen you put on windows to keep insects out. And that is near the belt and connected to this inner surface with some copper wires. Absolutely critical to the working of the Van de Graaff generator. Underneath, inside this base, so I paused because I decided that after showing you the brush here, that screen, I wanted to show you the brush in the bottom of the Van de Graaff. So I took it apart, I took the base off, and you could see that there is also a screen here, a brush, and the belt is right here on this electric motor that wheels it around. So there are these two brushes, and then the belt moving between them, and we're going to see how that creates a charge on the Van de Graaff. So we can get these out of the way again. So it's kind of like a little story of what happens to the charge. So you got this belt running, you see these arrows here, and what happens is step one, brush one down here, puts electrons onto the belt. And the belt carries these electrons up, and as the electrons approach the sphere, because it's negative, as it's charging, they're repelled away from the sphere. So they cannot jump on the outside. Okay, so it's kind of like, you know, electrons, if you could think of them as like having people qualities, then you would say they're like very antisocial. You let two of them go, they're going to race off to infinity to get as far away from each other as possible. So they don't want to be near each other because they repel. So this electron will not jump on the outside of the sphere because there's already a lot of electrons there, doesn't want to be near them. But what happens is it comes inside this sphere up here, and the electric field here is 0. And so because the electric field is 0, then step 3, the electron jumps off the belt, because see here it's next to other electrons on the belt, so it wants to get away from them, and it goes, hey, well, why don't I go here where the electric field is pointing, so the electric field is pointing toward these electrons in here, so it's going to go in the opposite direction. So it jumps on this brush to get away from the electrons on the belt. Now, once it's here, the electron, step 4, on the brush number 2, migrates to the outside of the shell because it's to get away from these other electrons here. So it's going further, trying to get further and further away. And then what happens is it comes from the inside to the outer surface. In a sense, it's tricked to a place of a lot of electrons. So again, if we could do this sort of personification of electrons, let's suppose there's 3 people in here and they behave like electrons. They want to get away from each other as far as possible. They're crashing into the walls, trying to get out. And then I open the door and I say, hey, go out in the hall because there's no one out there. And you look, the people look and they see there's no one, they can't see anyone out in the hall. They go through the door, round the corner, and the hallway's packed with people. They were tricked into a place, going into a place where there are a lot of electrons. Essentially, that's what happens with the Van de Graaff generator in the operation of this belt in these steps. Now, that's how it accumulates a charge. But then how does that charge go through air, which normally does not conduct electricity? So, why does this spark occur? Air is usually an insulator. So what I have here is the Van de Graaff generator building up this negative charge. And what happens is this other conductor through wires connected to the earth, as I mentioned, connected to the sink. And so the electrons, some of them in this metal, go into the earth, leaving it positive. So we've got this sort of a dipole, we would call it, and the electric field points in this direction towards the negative Van de Graaff. Now, the air is made of atoms which have protons and electrons. The electrons are orbiting around the protons. The protons in the atom are attracted to this negative Van de Graaff generator. They feel a force like this. While the electrons are repelled away from this Van de Graaff generator, they feel a force like this. So, the F on the proton pulls the proton toward the Van de Graaff. F on the electron pushes the electron away from the Van de Graaff. The F net is 0 on the air molecule. The analogy would be like this. I'm standing on a skateboard and people are trying to move me. One person pulls me with 1 Newton this way, another pulls me with 1 Newton this way. I'm going to stay at rest, right? 1 Newton, 1 Newton. So they pull harder. 2 Newtons, 2 Newtons. Why do they pull harder? Well, the Van de Graaff keeps building up charge, making more electric field, making these forces larger. So 2 newtons, I'm still at rest, right? No net force. So the Van de Graaff builds up charge, 3 newtons, 3 newtons. Okay, I'm still at rest. Keep going. 1 million newtons, 1 million newtons. What's going to happen to me? Split apart. And that's what happens to the air molecule. As the charge increases on the Van de Graaff generator, the F's increase also. Eventually the atom breaks, rips apart. The word we use for that, the scientific word, is ionizing. So it ionizes. And then there's a spark. Why is there a spark? Because this electron's now free of the atom. It's not locked in, so it shoots away and sparks into this. And so we get a discharge. The air becomes conductive. Now, the approximate electric field value at which air breaks apart or ionizes is 3 times 10 to the 6 newtons per coulomb. All right, so hopefully you enjoyed those very dramatic and beautiful shots of the Van de Graaff sparking, as well as this explanation of how it works. Fascinating device. I also want to send you to another day, and where I got my hair to stand on my head. So that was an interesting demonstration. And what you'll see there is that my hair will align with the electric field. You'll actually be able to see, visually see, when I had those diagrams, electric field's invisible. You can't see it around a proton. You could feel it, but you can't see it. But when I have my hair, and I'm going to charge myself up, my hair will align with the electric field. So you'll be able to see my hair, which is the pattern of the electric field. A lot of fun. So, again, brace yourself. Hello again, everybody. I'm going to do a few more Van de Graaff generator demonstrations, but I want to redo the hair charging experiment or demonstration. I remembered that I had a wig in the storeroom, and sometimes this works and sometimes it doesn't, to show the electric field lines with my hair. So we'll do that again before I go on to the new information. Just a couple more things about the Van de Graaff. The other thing that I forgot to mention in the last video is that I was standing up high on a milk crate because I wanted to be isolated from the ground. If I have my hand on this Van de Graaff and I'm standing on the ground, the charge is just going to go through my body into the ground, and I'll never build any charge up. So I want to be isolated from the ground, and that will allow the charge to build up and not leak away. So let's give it a shot and see if my hair stands up now. Okay, so here we go. I feel a little something. I think I see something reflecting in the Van de Graaff. Loosening it up. And again, the hair is hopefully aligning with the electric field lines. So my head is now a nice spherical conductor demonstrating electric field. All right, I don't know if it'll go anymore, but hopefully you see a nice little display of my hair. The other thing I want to point out is something else we're going to see in this video. Watch what happens when I stick my finger out. And you might even be able to hear the hissing out of my fingertip. And I make a blunt fist and it stops. Alright, so this seems to leak the charge away. Okay. Alright, so let's move on. Let me step off. Discharge. Shut off the Van de Graaff. Discharge it. Alright, so that was the Van de Graaff generator. We'll look at some more demonstrations with the Van de Graaff generator when we learn about voltage. Some surprising things about the Van de Graaff generator you'll learn there then also. But remember, The homework is not about the Van de Graaff generator. It's all about calculating the electric field with the formula then that I wrote earlier and the force from that formula, and then possibly using Newton's laws and kinematics to solve for analyzing the motion of the resulting particle. So I hope you enjoyed the video. I hope you enjoyed the demonstrations. I'll see you in the next physics video.